Hello, today I'm going to build a neural networks from scratch. To start building any kind of neural network, we need data. In this case, we need huge amounts of data of handwritten digits. First, we need to download these four files, which gives us 70,000 images with another 70,000 labels to work with. As I'm using Rust, I have to import this library to use these files. Next, we have to initialize the data and divide the data into training data and testing data. In this case, it is 60K images for training and 10K images for testing. Before we start building the neural network, we first need to understand the structure of the neural network. A neural network is a group of neurons that are inspired by the neurons in our brain. And the group of neurons creates a layer. There are three types of layers: input layer, hidden layer, and an output layer. And the goal of the input layer is to pass the input values to the hidden layers. Now let's take a closer look at the hidden layer. Let's say our neuron has two inputs, X and Y. And each of these inputs come with their own weights, and the neuron has a bias. To get the output Z, we multiply the input value with the corresponding weight, twice in this case, and then add the bias and pass it through an activation function. Then we do this for the entire layer using matrices. Then during training, we compare the output to the desired output to get the error gradient. And this entire process is called the forward pass. And this is only the first of two steps in machine learning. And step 2 is called the backward pass or backpropagation. The goal of the backward pass is to figure out exactly how much each weight and bias contributed to that error so we could adjust them. There are three main steps in backpropagation. Step 1. Remember how we changed the final answer using an activation function? In this step, we have to multiply the error gradient with the derivative of the activation function, and the result is called delta. Next, we have to do the same process to the hidden layers as well. But there's a problem. We don't have an error gradient to compare to. So we take the delta of the output layer, multiply its weights connecting to the output layer, and multiply that by the derivative of the activation function, and the result is called the delta of the hidden layer. Now we have to do step 1 for all neurons in every layer. Then we have to find the gradients of the weights and bias. To get the gradient for each weight, we have to multiply the delta with the input of the neuron. Remember when we were calculating the output, we added the bias? Because it has no constant attached to it, the gradient of the bias is delta itself. Now we reach the final step in training, which is to update the weights and bias. In order to do that, we have to multiply the weights gradient with the learning weight. And this result is subtracted from the original weights. And do the same thing to the bias. You might notice this new word called learning rate. This is a parameter that controls how fast your neural network learns. And repeat step 1 and step 2 thousands of times and you have a neural network that learns. Now we could start building the model. We have already initialized the variables here. Let's see if it works by printing out the information of the first image in the dataset. We can get the label by setting it to 0. And before printing out each pixel, we first have to normalize them. This is because the data comes from the form where the highest value is 255 and the lowest value is 0. But we don't need that. We want it so that the highest value is 1 and the lowest value is 0. Then we could print out the whole function in the main.rs file. While training a neural network, there's a lot of matrix multiplication, and instead of me implementing a function that does it from scratch, we can use this Rust library called NDArray, which gives us the function that can do this type of math really fast. But this comes at a cost. This library uses a different type of data structure which is optimized for matrix multiplication, and so we have to convert the vector data type to array data type that NDArray uses. When creating a neural network, we need to organize the weights and bias. So I have created a struct called layer to store them all. I have also created a function where when we create a new layer, it comes with random numbers, and during training we could adjust them accordingly. Next, we need math, like function that does the matrix multiplication so our code looks cleaner. We could create a math.rs file and add all the functions there. like this function that multiplies two arrays with different dimensions, and some other functions for the future like multiply, same, and add. Now we could write the training logic, which is surprisingly simple. The entire logic boils down to a simple for loop. In this function, we first have to initialize the input data, and then we start the calculation by multiplying the input value with the weights of the first layer and add the bias to that result. Then we do the same thing, but instead of using the input data, we use the previous result and add the bias, and repeat the same step again to get the final output layer. And at the end, we return the output. Let's test the code out for the first image, shall we? And this prints out exactly what we want. We can also see how fast it takes to calculate one image, and it's 5 milliseconds. Before we continue, I might have forgotten an important part of a neural network, which is the activation function. There are many kinds of activation functions in math, like the sigmoid function, ReLU, softmax, and etc. And I'll be using ReLU. Let's go back to math.rs file and create a ReLU function, where if the value is greater than 0, then it returns the value. And if the value is less than 0, it returns 0 instead of the value. Next, we have to create this number called cost. This number tells us how good or bad our neural network is doing. To get the cost, all we have to do is subtract the prediction of the neural network from the expected output, and then square the result and divide that answer by 2. Then we could finally start correcting the neural network's mistakes by using the backpropagation algorithm. First, we need to get the error gradient, which is just the neural network output and subtracted by the expected output. And then we have to find the derivative of the activation function. Then we multiply the error gradient with the derivative of the activation function and multiply that result with the inputs transposed. And this gives us the weights gradient. And the gradient for the bias is delta itself. And do the same thing for the other layers as well. And at the end, you will have weights gradient and the gradient for the bias. To get the new weights, we have to multiply the weights with the number called the learning rate, and then add the result to the original weights, and do the same thing for the bias. But this method is slow. So what we have to do is, instead of feeding each image, we send batches of images to the neural network. This is faster because it lets your hardware process multiple images simultaneously as a large matrix multiplication. To make this happen, we only have to change the dimension of the data type from dimension 1 to dimension 2. Now we train. As you could see, even with this new method, it's still slow, but there's a cool fix for this. In Rust, there's this function called cargo run dash dash release. This is a fancy function of the regular cargo run because it makes the code run very fast, with a drawback where the compile time being slower. If we run this, there's going to be a noticeable difference, as you could see here. Now we test the model. This part is very important because there is a phenomenon called overfitting, where instead of the model learning, it memorizes the answers, which is bad. Luckily for us, the model did not memorize the answers. After this, you could do whatever you want with the model, and I made it so that you could train, and after that we could save the weights and bias into a JSON file for later use. And also I created this drawing window to use those weights and bias to predict the digits. Let's test it, shall we?